subject mathematical foundations for computer science. So under that today, so we will discuss about the mathematical logic and proposition for first order logic. Okay, so we'll start the session. Okay, is PPT is visible for you? Hello, please give me a response.
Yes, sir.
Yes, ma'am. Thank you a lot. So just 1 second, we'll have small. One second, ma, I will start. Okay, is PPT is visible? Okay. Yes, ma'am. Hello. మా PPT visible ఉందా?
Yes, sir.
Yes, ma'am. Thank you. So today, the topics outline are like this. What is proposition? Different types of connectives, well-formed formulas, tautologies and duality law, normal forms, two types of normal forms, PDNF, PCNF, inference theory, indirect method of proof, quantifiers and free variables and bounded variables, and the last we have inference theory for predicate calculus. So first coming to what is proposition. So given any statement, any declarative statement, which is either true or false, but it should not be both, is called as a proposition. Okay, given any statement, it should be decided, it is possible to decide that it may be true or false. So that kind of statement is called as proposition. Let us see the examples here. Here we have the examples for proposition. So Delhi is the capital of India. So it is the statement is true. Kolkata is a country. It is a false. 5 is prime number. It is the true. 2 plus 3 equal to 4. So it is false. So these statements can be decided either true or false. So that this can be treated as a proposition. Coming to this side, here these are the examples for they are not propositions. So for example, if you see the third statement, x plus y is equal to 5. So here I cannot say that it is always true or it is always false. Based on x value and y value, it will become 5. Suppose if I given 2 plus 3, it will be 5. Suppose if it is 2 plus 4, it becomes 6. So that I cannot say that it is a true or false. So these kind of statements, how beautiful are, wish you happy new year. Suppose if you see the statement wish you happy new year, it is valid or true only on the January 1st only, and the rest of the days it is not true. So take one book, it is it is a kind of action. So that kind of statements also not considered as a proposition. And we may found two types of propositions, like atomic propositions or compound propositions. Atomic proposition means the propositions which will contain only one statement, one declarative statement is called as atomic propositions. Whereas the compound propositions mean they will contain two or more statements or two or more number of propositions. For example, for atomic proposition, 7 is a prime number. So this is only one statement. And whereas the compound proposition, here I can consider example 2 plus 3 equal to 5, 4 minus 7 equal to 10. These two are combined by using the word and. So now 2 plus 3 equal to 5, 4 minus 7 equal to 10. These two are the propositions which are combined by using the and word. So now here, what is the point is that So if you want to create compound propositions, so then we need to go to use logical connectives. So in propositional logic, so we are going to use some words which will be used to connect two or more number of propositions is going to be called as a connective. Sometimes it may be a single word, or sometimes it may be a phrase, or sometimes we may represent by means of symbol. So whatever it is, what we'll do there is we are going to use those symbols or the words to connect two or more number of propositions. They are going to be called as a connectives. Now see here, uh, we are going to discuss five connectives, mainly negation, conjunction, disjunction, conditional, and biconditional. So coming to negation, suppose if I want to connect, or if it is actually one of the connect which can be used only with one statement. Okay, so if I want to negate, or if you want to add a word not, it is not the case that like that before any statement, then I may go to use this negation connective. Suppose if you are representing the given proposition p, so then the negation of that particular statement p can be represented as negation p. Okay, so I may represent like this, and this is the truth table related to this. So if given proposition is true, it becomes false. If it is false, it becomes true. Suppose if you see the example here, Kolkata is a city. So negation p means Kolkata is not a city, or sometimes I may use like this, it is not the case that Kolkata is a city, like this. And coming to the second one, the conjunction connective. See here, if I want to connect two or more number of statements by using the connective, by using the word and, or sometimes I may use but. Okay, P and Q, or P but Q, like this. So then I am going to use this conjunction connective. And coming to the truth table, so if you consider two variables as example, so 2 power 2, so totally four possibilities will get here. So the four possibilities will be like this. Now coming to this one, when it will be true and when it will be false. So whenever both the truth values are true, both the proposition truth values are true, then only it will be true. In all other cases, it will be false. In the simple terms, we can remember it as a multiplication operation. Okay, so true and true means you may assume it as one, false means we may assume it as 0, and we can construct this one. Let us see this example. Let us P is it is raining today. Q is there are 10 chairs in the room. Then P and Q means I can write like this. It is raining today and there are 10 chairs in the room. So like that I can connect two statements by using conjunction connective. And coming to disjunction connective, so the disjunction of two statements is going to be represented as P or Q. Okay, so if you want to combine two propositions with the word or, either P or, either or. Okay, simply or, sometimes I may use either or. So then I am going to use this disjunction connective, and it is represented like this. And coming to the truth table, so we will consider two variables PQ, and the truth table will be like this. Okay, so here the point is that when it will be false, whenever both the proposition truth values are false, then only it will be false. In all other cases, it will be true only. And this disjunction connective, we may assume it as a addition operation, and we can easily trace out this. Let us see this example. I have two statements. I shall go to the home. I shall go to the game, or Q is I shall watch the game on television. So now both are combined by using this or. I shall go to the game or watch the game on television, like this. And coming to the conditional connective. Okay, so here if two propositions, let us P and Q are the two propositions, and if we want to connect those two propositions with the meaning if then Q, so then I am going to use this conditional statement or implication statement. So conditional statement is also called as implication statement. And here, and it is denoted as like this, P implies Q, like this. Okay, and here there is some specific name for P and specific name for Q proposition. So P is also called as hypothesis or premise or antecedent, like that we can call it as a P. Similarly, Q can be called as a conclusion or consequent. Okay, remember this one. And coming to the truth table, so you observe false. Okay, so when it will be false. Okay, if you see there, if the first proposition is true, second proposition is Q, then only it will be false. In all other cases, it will be true only. Let us see this example. I have two propositions. The first one is the crop will be destroyed. Second one, there is a flood. Now, whenever we are combining the two propositions of any kind, so you need to be careful that we need to get a proper meaning. So like that you have to combine. Here I used this if then. So if there is a flood, then the crop will be destroyed. So that whenever we are combining two statements by using any of the connective, you should note that there should not be any problem or there should not be any disturbance in the meaning of that one. Okay. So like that you have to take. And see there, so this is the normal points that we know already. And coming to this conditional connective, there are some more points also, they're very important. Normally, this P implies P means we always think that if P then Q, only that is the only statement that we'll observe here. But there are some other statements that also come under this particular category. P implies Q. Okay. So given any statement, if you want to represent or if you want to do some processing, so then you may found the words like this, then also it will represent this particular implies. So if P then Q, that is the well-known one for all. Similarly, P implies Q. So that is the second one. That is a normal. Okay. And Q follows from P. Suppose if you found the word follows from. Okay. So it is a follows from. Q follows from P. Then also you can use implies. Q if P. Q if P. Q when P. Q whenever P. See there, in all these statements, Q is coming first. Okay. Q follows from P. Q if P. Q when P. Q whenever P. P only if Q. It is different. P is sufficient for Q. Q is necessary for P. Q without P is possible and can exist. P without Q is impossible and cannot exist. So that here, if you see these words, whatever the words I represented, whenever we found these words, then they also can be represented by using conditional connective. Okay, and see here, it is an important point is that so sometimes there is a confusion and by mistakenly we may use conditional connective, but that conditional connective we need to use in the proper way. Suppose if you have a statement P unless Q, it should be written as negation Q implies P. P unless Q. Okay, so then it is the meaning that are implied by using conditional connective we will connect like this. And this is the important two formulas which is equivalent to conditional connective. So we are going to use like this. P implies Q can be written as negation P or Q. Similarly, negation Q implies negation P. These two are the equivalent formulas P implies Q. And coming to the biconditional connective, okay, see there we have two propositions once again. If we want to connect those two propositions with the words like this, P if and only if Q, okay, so then I am going to use this biconditional connective, and this is will be represented by means of by implies symbol. And coming to this truth table, it is important here, and you have to observe here carefully that so whenever the truth values are same, whether it is a true or it is a false, the final truth value is true only. Whenever the truth values are different, either true false or false true, then the truth values are false. So that is the truth table related to biconditional connective. See here the example letter. One of the proposition is a polygon is a triangle. Other proposition is a polygon has exactly three sides. Now here these two statements will depend on each other, so that I can connect these two statements by using if and only for biconditional connective. So if you see here, these two statements can be connected like this. A polygon is a triangle if and only if it has exactly three sides. So if a polygon is a triangle means it should have exactly three sides. And vice versa, if any polygon is having three sides, then it can be treated as a triangle. Like that we can say about this, but we can consider example for this biconditional connective. And coming to this one, this biconditional connective can also be used in some other places. So where we found the words like this. Normally we know only about the if and only if. Okay. So apart from that, if we found the words like this, then also we may use biconditional connective. See here, if P then Q and if Q then P. So not only if and only if, we may found if P then Q and if Q then P. Then also I can use. Next, Q if and only if P. Next, P is necessary and sufficient for Q. Next, Q is necessary and sufficient for Q. Okay, and P and Q are necessary and sufficient for each other. P and Q cannot exist without each other. Either P and Q both exist or none of them exist. P and Q are equivalent. Negation P and negation Q are equivalent. So like this, if we found the words or phrases like this, then also I can use this biconditional connective. See here, the equivalence formula this for this biconditional connective is, so which is well known, this one, P implies Q and Q implies P. This is actually this here whatever the statement we have, so P implies Q and here Q implies P, so that is actually equal statement or meaning for this. Similarly, P and Q are negation P and negation Q, so these two are the equivalent formulas related to this biconditional connective. So these are related to this connectives and what are the proposition. So is there any doubts up to now regarding this? If you have any doubts, just you can raise, or otherwise we'll continue. Is there any doubts now? Okay, next we move to another topic. So this is regarding converse, inverse, and contrapositive. These are important terminologies with respect to this conditional statement. So we have conditional statement P implies Q. Okay. So related to this conditional statement P implies Q, I can write three different conversions for that one. Let us see here. So as we already told that P implies Q means P is called as hypothesis or premise. Q is called as consequent or conclusion, like this. So if you are going to change the roles of this hypothesis and consequent or conclusion, so then this will come under here. So see here, P implies Q. If you are going to, hello. So Q implies P. That means if you are changing conclusion and hypothesis in the reverse, then we'll get converse. And if you are applying negation for both, so then we'll get inverse. And we are applying both, that is, we are changing the roles, as well as if you are going to apply that particular negation for both, then it will become contrapositive. So let us, the statements we have here. So if you have the two statements, that is, if it rains, then the crop will grow. So converse is just the crop will grow, then there has been rain. Inverse is if it does not rain, then crop will not grow. Not will be added on the both sides. Contrapositive. So it is a contrapositive. So we need to reverse the roles, as well as we need to apply the negation for both. So then we'll get like this. So these points we know already very well. And coming to this one, this is very important here. So here, we constructed the truth table for these things. Let us see here, the truth tables are like this. So here, this is the truth table for converse. So here I have for implied statement. So we know PQ, P implies Q means true, false, true, true. See the converse truth table will get like this: true, true, false, true. And similarly, I can construct for inverse truth table: true, true, false, true. For contrapositive, the truth table will be true, false, true, true. Now here the point is that we need to observe the truth tables of these four. Okay, let us see the truth table for converse and inverse. So here we got true, true, false, true. Here also true, true, false, true. So that converse and inverse are equivalent to each other. Okay, that means what we can say is Q implies P is equivalent to negation P implies negation Q. So that is the one important point. Next, second one is P implies Q and contrapositive are equivalent to each other. That means P implies Q. Here the truth table is true, false, true, true. Here for negation Q implies negation P, the truth table is true, false, true, true. So both are same. So that what we can say is P implies Q is equivalent to negation Q implies negation P. Actually, this is what the equivalent formula we represented previously. Okay. So if you observe these two are same. Okay. So P implies Q means P implies Q is equivalent to negation Q implies negation P. Q implies P means negation P implies negation Q. So inverse for each one. Okay. So like that we can find the points regarding this one. And coming to the last important point with respect to this. So if you are going to do any two actions, always it will result in the third one. Okay. See what is the meaning of this statement. So inverse of converse is contrapositive. Okay. So inverse of converse. So let us see here the converse is actually the statement is P implies Q. For that the converse is Q implies P. Okay. So what we are doing, so converse, inverse of converse. So for this the converse, inverse means negation Q implies negation P. So what happens is contrapositive. So contrapositive means, so negation Q implies negation P. So that if you are doing any two actions combinedly, it will result in the third one. Okay. For you can go with any combination. Let us, if you see this contrapositive, for contrapositive, if you apply inverse, it will result for converse. So here contrapositive is negation Q implies negation P. So for this, if you are applying inverse means what happens? Okay. So we need to apply negation for both. So negation of negation will get Q and the negation of negation P will get P. So what it is? Q implies P. So there is nothing but your converse. So like that we can find some points regarding converse, inverse and contrapositive. And coming to this tautology, contradiction, contingency. So this is related to this one, very important. See here, we know very well already, any formula, any given formula for which if you are getting true for any possible truth values, for all possible truth values, then we are going to call it as tautology. Okay. So here given the formula like this. So here we have two variables. So the two variables mean four combinations will get here. So if you construct the truth table for the given formula, so for all possible four cases, here these are the four cases. What we need to get at the last is we need to get true. So then it is going to be called as tautology. Okay. Now regarding this tautology, so there is one point important to that. So all tautologies are valid. Valid in the sense that is true. That is a correct statement. And unfalsible, unfalsiable, unfalsifiable. So false means that is a opposite to true. Unfalsifiable means so that becomes true only. Okay, that means all tautologies are valid and unfalsifiable and vice versa. And that means we can go for in the reverse. But all tautologies are satisfiable. So all tautologies we can satisfiable, but not vice versa. Okay. So all satisfiable statements will not become tautologies. So this is the point that you have to remember. And coming to contradiction, so similar to the tautology. So given any formula, for that formula, if you are going to apply truth values, for all possible truth values like this, true, false, true, false. So if you are getting false as the final result, then it is going to be called as a contradiction. Okay, now regarding this contradiction, so see there one important point. So whatever the contradictions we are considering, they are all invalid. Tautologies are valid, contradictions are invalid and falsible, but not vice versa. That means all false statements cannot be contradictions, and all contradictions are unsatisfiable. Okay, so if you see any contradiction statement, that can be proved as an unsatisfiable statement, but vice versa also possible here. And coming to last one, contingency. So if you are given any formula, if you are going to construct the truth table for that, so if you are getting combination of both true and false, that means I cannot predict whether it is a true for all cases or whether it is a false for all the cases. So then it is going to be treated as a contingency. Okay. So now related to this, again the statement we have, all contingencies are invalid and falsible, but not vice versa. And all contingencies are satisfiable, but not vice versa. Here we can prove that all contingent statements as invalid, as well as all contingent statements are satisfiable, but vice versa is not possible. So this is regarding the three: tautology, contradiction, and contingency. And coming to these, some important points are there. We can easily identify, just I can say that these are the tricks that we can easily check whether they belong to tautology, contradiction, contingency, or valid, invalid, satisfiable, unsatisfiable, like that, by just constructing the truth table. Let us see here, if we want to prove any one of them as a tautology or valid or unfalsible, so then we can construct the truth table. From the truth table, we need to find that the last column. Okay, in the last column of the truth table, only true should be there. Then it may be a tautology, or it may be valid, or it may be unfalsifiable. And coming to contradiction or unsatisfiable. So then, if you construct the truth table, the last column will get always false. Coming to contingency, so we will get both true and false. And coming to invalid and falsifiable. So these three are very easy to remember and understand. So these two are somewhat just tricky that you have to remember. So if you want to check whether it is invalid or falsifiable, so then we can check it. It contains either only false. Okay. So if your truth table at the last, if it is having only false or both true and false, so then that proposition may be treated as a invalid or falsifiable. Coming to the last one, satisfiable. So it should contain either only true or both true and false in the last column. So then I can say that the proposition is satisfiable. So this is regarding that particular what we can say about tautology, contradiction, contingency. Similarly, the other terminologies related to that. Okay. So is there any doubts regarding that?
No, sir.
No. Okay. Thank you, ma. I will go. Okay. Coming to this well-formed formulas, the next important one. So actually, the well-formed formula means they are nothing but the propositions with some other components. So by default, any true statement or false statement, I can consider it as a what we can say true or false, or by individual propositions also well-formed formulas, or by using connectives. If you are going to combine two or more number of statements, they are also called as well-formed formulas. In addition to that, if you are going to connect with any quantifier, so universal quantifier, existential quantifier, then also it will be treated as a well-formed formula. So the rules, whatever we have A, B, C, D, four rules. So if you are following, if you are going to construct any compound proposition by using any of these four rules, then that is going to be treated as a well-formed formula. So now here, normally the problems we may found here is we need to check out whether two formulas, two well-formed formulas may be equal or not. Okay, so this can be implemented by using two methods, or we can identify by using two methods, truth table method or replacement process. So I can say that truth table method is shortcut method and easily you can do that. Suppose let us if he is asking for to prove P implies Q is equivalent to negation P or Q. So just construct the truth table for P implies Q as well as for negation P or Q. See here for P implies Q I constructed and for negation P or Q. So if you are getting same truth values, true, false, true, 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 false, true, true. So then simply I can say that they are equivalent. And the other method is other approach is so they will be connected by means of biconditional. After connecting by means of biconditional, if you are getting all the truth values as true, that is tautology, then I can say that they are equal. And there is another method that is a replacement process. So in this replacement process, we are going to use a different formulas or laws, which will be used whenever we are deriving that particular given formulas to another one. So let us see here, this is idempotent law, PRP equal to P, P and P equal to P. Associative law, PRQ or R equal to PRQRR. Similarly, another one, commutative law, PRQ equivalent to QRP. Similarly, for AND operator, distributive law, this very important one, PRQ and R equal to PRQ and PRR. Identity law, P or false equal to P, P or true equal to true. Similarly, the other two component laws, P or negation P true, P and negation P false. So this is double negation will result to the normal P. And absorption law, these are again important. P or P and Q becomes P and PRQ becomes P. De Morgan law, this is also very important. Negation of PRQ equal to negation P and negation Q. Negation of P and Q equal to negation P or negation Q. So if you have here and R, it becomes and. If you have and here, it becomes R only. And just small two problems examples I can consider. So let us see here. PRQ implies PRQ. Sorry, P and Q implies PRQ that I want to prove. Okay, so now you assume it as P and you assume it as Q. So according to this P equivalent formula, so I can write it as a negation P R Q. So okay, so negation of P R Q. So if you apply De Morgan law, we will get like this, and this one P R Q will be as this. And here, as we have same symbols in the cases, we can rearrange the values. Finally, it will become true. So that it will be finally it is true means I can say that it is tautology. Suppose if I want to prove that both are equivalent. So now see here the another example. P implies Q and R implies Q. So implies formula, I can apply this formula once again. Negation PRQ and negation RRQ. And so here if you see there RQ both the same. Okay. So that negation P and negation RQ. So it can be negation P, PRRQ, and it can be written as it is negation PRQ. So that PR implies Q, I can write like this. So that is equivalent formula what we need to get. So like that I can derive. And coming to another one, that is a duality law. So when two formulas are said to be dual to one another. So let us given two formulas A and A star. You assume that two formulas are there, A and A star. Now these two formulas said to be equivalent to one another. When they will be said to be equivalent to one another is. So we need to do two steps. So if you are going to replace with and with and with or and or with and, similarly true with false, false with true. Okay, so then the resultant formula what we are getting is going to be called as dual to another one. Let us see here, we have the formula here like this, P R Q and R. So the dual for that is P and Q R R. Similarly I can write, so here I have true, here I have false. So this R becomes and now. Okay, like that I can consider. So there is a small important point is that how we will get the negation, that is a dual for given formula is. So if you are going to apply negation, okay, that is the formula given is A, and if you are going to apply for the negation for that formula, then whatever the result we are getting, that result becomes dual for the given formula. That is a simple way to get to identify the dual for the given formula. And coming to this one, it is a tautological implication. So when we can say that, let us given two formulas A and B, when we can say that A is tautologically implies B means, so if you are going to construct the truth table, okay, for the two formulas, let us here P implies Q is one formula, negation Q implies negation P is another formula. So if you want to prove that A is tautologically implies B, so just you combine these two formulas by using implies, that is a conditional connective, and prove that it is a tautology. So if you are getting it as a tautology, then I can say that, so that A formula will tautologically implies B formula. Okay, so like that I can prove this one. And the next one, normal forms. So it is important one. Okay, see here, we have two normal forms are there. So like principal disjunctive normal form, next to principal conjunctive normal form. Before discussing these two normal forms, we need to know what is this conjunction, or that is elementary products, elementary sums like that. So the conjunction of the variables and their negation in a formula is called as a elementary product. Okay, so let us P and Q are the two propositions. The conjunction of that two variables, either in the normal form or negation form, we can call it as a elementary product. Similarly, disjunction. So if you are going to combine two, that is variables, either P, Q or negation P or negation Q, by use this disjunction, then it will be called as a elementary sums. So based on this, I can have two normal forms, that is a PDNF and PCNF. Before discussing that, just see here disjunctive normal form. So what is this disjunctive normal form? So a statement formula which is equivalent to given formula and which consists of sum of elementary products is called as a what we can say, that is a DNF. So we already discussed the elementary products. Okay, so sum of elementary products. We are going to combine elementary products by using the this particular what we can say, that is R. So then I can say that that is going to be disjunctive normal form. Okay, So this is one term, product term, and this is one elementary product. This is one elementary product. They are combined by using sum. Okay. So now it is going to be called as, now it is said to be in disjunctive normal form. So given any formula, we can represent that in disjunctive normal form. Let us see here the normal process to represent any formula either in DNF or CNF is, first observe in that one, is there any by implies is there? You apply the equivalent formula for that. Similarly, implies is there, you apply the equivalent formula there. After that, normal we may found negation, we apply De Morgan law equivalent for that. So that finally will it will be get into the either in elementary product term or elementary sum terms. So here P and P implies Q is there. So P implies Q is written as negation P or Q. So here P and negation P, P and Q. So P and negation P false, and P and Q, finally P and Q. Now here I got only one product term, no problem. So sometimes we may get two or more product terms, then they are summed with, they are combined with some operation. Similarly, CNF, consecutive normal form. So any statement formula which will consist of product of elementary sums is called as what I can say, that is consecutive. Then we can say that it is in consecutive normal form. Let us see here, this is the example. So these are the elementary sums. They are combined with the product. Okay. So now these are another example. Now see here the same what we considered previously. So that is P and P implies Q. Now P and this one negation P R Q. For P implies Q, I can write it as negation P R Q. Okay. So now this is one product term. Sorry, this is one sum term, and this is another sum term. Okay. So now I can say that this is what we can say the required consecutive normal form. Now, based on that DNF and CNF, we may go to principal disjunctive normal form. Similarly, principal uh, consecutive normal form. So first we'll see what is this PDNF. So for any given formula, just I can say the previous whatever that we have there, so I can go to represent like this. So it is nothing but again once again sum of products. Okay, sum of elementary products. But the products here I am going to represent it as a min terms. Okay. Now what is the difference between the previous one and this one is, so we need to have all the variables or all the propositions, whatever we have there, that should be there. Okay. So then it is going to be called as a min term. So let us see here P R Q, sorry, P and Q, P and negation Q, negation P and Q, negation P and negation Q. So like that we need to have. So for this is for two variables and this is for three variables we can consider. Now let us see here the problem for the given formula. How can we found what we can say that is a PDNF? So just what we have to do is first you construct the truth table for that. Okay, this is a given formula. It is actually the easiest method that we'll follow, or we can follow by using the formulas also. See here, given any formula like this, so you just construct the truth table. Okay, after constructing the truth table, you just try identify the rows which are containing true as the truth values. Okay. So now related to that, you will find the min terms here. Okay. So previously PDNF means we told min term, no. So the min terms that we have right here. Let us see how I am writing here this min terms. Uh, these are three variables we have, so that totally 8 possibilities will get here. So true, 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 true. Again, 4 falses. True, true, false, false, true, true, false, false. So like that, once you written here, the min terms will be written here like this. So if you have true, it will be represented in the normal, and if you have F, it will be represented in the negation form, and they will be combined with this and. Okay. So now P and Q and R, P and Q and negation R, negation P and Q and R, negation P and negation Q and R. So these are the four terms that will be present in your PDNF notation. So, hello, now please mute your mic. Okay, so this is the way how we are going to find that particular in the simplest way to find the PDNF form. Okay, so next this is actually the by using the formulas what we discussed previously. I can go to find out the equivalent formula for that one. Okay, so just as I already told, try to remove the implies. By implies we have there, implies will be there. negation will be there. Try to remove one by one so that it will be get simplified. So here we have this one. So P implies Q and negation of negation P and negation Q. So first I am applying for De Morgan law for this one. Now this
Cutout.
becomes PRQ, and later on I am applying for P implies Q. It
Excuse me,
becomes
sir.
yes. Yes, ma చెప్పండి.
సార్ వాయిస్ కట్ అవుతుంది సార్.
వాయిస్ కట్ అవుతుందా? ఓకే. Yes. Is it clear now?
బ్రేక్ అవుతుంది సార్.
Okay. Is it clear now? హలో, ఇప్పుడు క్లియర్ అన్నా?
ఎస్ సార్.
Okay. Okay, now here first I removed PR. I applied De Morgan law for this. Now it becomes PRQ. Here P implies Q is there. Now it becomes negation PRQ. Okay. So after that, now I am considering this P, this as P, and this entire thing as Q. That is P implies Q. So now negation P or this entire formula here. Now I am applying distributive law here. So I will get this one. So like that I can get up to negation PRQ. So now this is actually in DNF form. Okay. So why? Because so DNF means sum of products we need to have. Okay. But here I have only negation P or Q, that's all. So in this one variable is missing, and in this another way. So here Q variable is missing, here P variable is missing. Okay. So that to provide that, what we are going to do is I will add true, false, true, truth value, so that if negation P and true means, again it will become negation P only, so that it will not be modified. So that in the place of true, what I am doing, I am going to add the variable which is missing in the form of Q or negation Q. Similarly, in the second expression, Q and true, so in the place of true, as a P variable is missing, I am introducing this one. So that if you are applying once again distributive law for this, I will get finally PDNF for this one. So like that I can do. But this is very difficult process. As the time is a constraint, it is a required, or it is a preferable that just try to go with the truth table method. But in this method, what we have to do is we need to take care while writing either the true or false or min terms, whatever they. Okay. Now in the PDNF, you have to remember that which rows you have to consider. That is the rows which are having truth value. And in the min terms, how we are writing the min terms means true means we'll write in the normal form, false means we'll write in the negation form. So after the constructing the truth table, just you combine the min terms which are in the rows of 2 by using this R symbol. So that will get that particular equivalent PDNF notation. Okay. So we can do this one also, but it is time consuming process. We can go with the truth table method. And similarly, the next one is a PCNF method. So now here PCNF means, so here we are going to use a term called as a max term. Okay. Product of sums previously. Okay. Previously sum of products. Now it becomes product of sums canonical form. Okay. So here I have the max term. That means every term should have all possible variables, either in the normal form or negation form. Okay. So then we can have that max term, and that some product of all these max terms we are going to call it as principal consecutive normal form. And see the small example. If I is asking to find out the equivalent PCNF for the given formula, just what we have to do is we need to construct the truth table. It is very simple to construct the truth table. So once we constructed the truth table, just we found the rows which are having false truth value. So this is the important point. Okay. So previously we considered the rows which are having true truth value, but here we need to consider the rows which are having false truth value. And one more point is that previously we've written true means in the normal form, false means in the negation form. But here true means we need to write in the negation form, false means we need to write in the normal form. So now according to this, just here I didn't written max terms. We need to write max terms here. So according to this one, so negation P or negation Q, and this is negation P, sorry, this is not required, and this one is P or negation Q, and this is P or Q. So now if you combine those three, so we will get the required PCNF notation. And this without constructing the truth table, we can do the for the same problem we can do like this. Okay, so just as I already told, first remove the implies, so this becomes negation PRQ. Apply De Morgan law, now it becomes P and negation Q. So now here it is one sum term and this is another sum term. Okay, so in the first sum term, okay, we have Q variable is missing. Here in the Q variable is missing. Here P variable is missing. So that I will write like this. So here previously we introduced a true truth value. Okay, if you observe the problem there, in the PDNF we introduced the truth value, but here we need to introduce false truth value so that the value will not change here. So now PR false. Now in the place of false, the variable which is missing, we'll write that. So after that we apply the distributive law and the other laws. So finally we'll get like this. Okay. Here in this one also, it is preferable to follow truth table method, either PCNF or PDNF, but you have to carefully write or carefully construct the truth table. And coming to the last point here, so here what is the thing is, given a problem or given a formula either in PCNF notation or in PDNF notation, if you are asking to convert to another one, okay, that is from PCNF to PDNF or from PDNF to PCNF, so we may do that very easily. Okay, so what is the process is, suppose you are given a formula, okay, given a well formed formula here. Now for that, we are identifying first PCNF. So let us, the PCNF is having 3 terms. We will assume that 3 terms are there. Totally 8 terms are there. You assume like that. Now the PCNF we got here 3 terms. Now, so the rest of the terms, okay, here we got the 3 terms. So rest of the terms in PCNF is 5 terms here. Okay. So now we need to identify that rest of the 5 terms, and for that we need to apply negation. So if you apply negation, whatever the result we are getting, that becomes your PDNF. Okay, this is the process that what you have to do here. Okay, so I repeat once again from PDNF now. So first we will give a problem. So directly if they given PCNF or PDNF, we will directly do that. Okay, suppose if you are given PDNF. Okay, so now let us assume that six terms are there. Okay, so totally 8. Here PDNF got 6 terms. Now the missing terms are there. How many missing terms are there means only 2 terms are there. For this you apply the negation. So if you apply the negation, then now the result becomes your PCNF. So this is based on the assumption that, so given a formula, if you apply double negation, we'll get again to the same result. So with that idea, we can convert from PCNF to PDNF or PDNF to PCNF. Okay, let us see this here, the small example. Okay, here also we can follow the truth table method. Okay, so in the truth table method, I can directly write max term or min term. Okay, so just construct the truth table. If you need max term, that is a PCNF, just we go with the false rows. If you need, that is what we can say, that is PDNF, we go with the true rows. Whatever the rows we have true related to that, we will identify the min terms and they will be written directly. That is the simplest way. Or otherwise, if you have the formula like this, let us here, this is the problem given. Now it is simplified. And finally we got, so let us observe here, it is containing 3 variables. So for 2 power 3, totally 8 terms will get there. Now in the PCNF, I got only 1 term. So that in the PDNF, how many terms will have there is, we have 7 terms. But how we will identify that is, so this is the term we have there. Now, what are the missing terms that we have to write here? So this is the term in the PCNF. So the missing terms will be like 7 terms are like this. Okay. Now, once you written the missing terms for this, now we will apply the negation of this missing terms what we got here. So now whatever the result we are getting here, so negation means De Morgan law, just we can easily apply that. Whatever the result we are getting at the last, that becomes your required PDNF. Similarly, vice versa, we can apply this particular process. So this is the way how we are going to convert from PCNF to PDNF or from PDNF to PCNF. Okay, ma, is there any doubts in this? Up to now, is there any doubts? Okay, so we go with the next. Only few topics are there. Just please be stay in the session. So next one is inference theory. Okay, this is the important one, which may have the questions from this one. Okay, what is the meaning of inference theory? Okay, given set of some propositions or hypothesis, I may call it as a propositions or hypothesis. From that, what we can, so let us P implies Q, negation P R. So these are all called as a hypothesis or proposition. Let us from this I want to derive to some C. Okay, hypothesis I may write H1, H2 or premises like this. So from this hypothesis, if you are trying to derive to P implies R, now whatever the process, whatever the rules we are applying, whatever the techniques we are going to follow here, that are all called as a inference theory. And it can be written simply in the form of notation. I can write like this: H1 and H2 and Hm all will be derived to the conclusion C. Okay. And here, if you want to do this, or if you want to derive the conclusion from the set of premises, we may go to use the rules like this: rule P, rule T. So rule P means in the derivation process, I may add any of the proposition. Rule T means I may apply any equivalent formula. So which we already discussed previously, are the formulas whatever we have here. These formulas may be used in the derivation process. Okay, so rule P means I may add any proposition, or rule T means I may apply any formula, equivalent formula. These implication formulas are the equivalence formulas what we discussed previously. Now let us see here a small example. Suppose the problem is given that, so P R Q and P implies R and Q implies S. Okay, these are the given hypothesis premise. From this, we need to check that whether this S or R is logically derived or not. Okay, so first what you have to do is we need to follow, or we need to consider the hypothesis in such a way that it is possible to apply the rules or the equivalence formulas what we discussed previously. Now see here, first I am introducing this PRQ, and equivalent for that by P implies Q equivalent formula I am applying here, so that it is rule T. So actually, while in the examination no need to do all this. Okay, so now this is the result we have now. Now I am applying Q implies S. Okay, from 2 and 3. So P implies negation P implies Q, Q implies S. Now this Q get cancelled, negation P implies S is the result. So that I am considering here rule T. And now I am introducing the another one. So now this negation P implies Q can be written as negation S implies P by following this particular formula. So now after this, I am applying or I am using this P implies R. So S negation S implies P, P implies R. P get cancelled. Negation S implies R will get here. So finally, this can be written as SRR. So SRR is whatever the conclusion what we require. So like that. So actually, these all things are not required. Just what we have to do is we need to derive by using all the propositions, hypothesis given to the conclusion. And similarly, I may use one more rule that is called as a conditional proof or rule CP. What is the meaning of this one is, let us see this one. Suppose if you are asked to derive, okay, if you are asked to derive R from the set of, if you want to derive S from R and set of premises, now it can be derived like this. R implies S can be derived from the set of premises. So if you follow this particular logic, then I can go to use this. Let us see here. So suppose the problem is given like this. Now it can be rewritten like this. Let us see this. Show that R implies S can be derived from the premises. P implies Q implies S. This is one hypothesis. Negation RP, this is another hypothesis. And Q is another hypothesis. Now this is the conclusion that we need to derive. Now instead of deriving this R implies S, now what we can do is this R can be added as, that means the premises whatever we have, that can be added as additional premise, and we can derive this particular process. And this is the process what we know already, what we discussed already. We can go as usual. And this is consistency of premises. Now what is the meaning of this consistent? Okay, simply I can say that by using set of premises, okay, if you are going to derive to true, so then that is going to be called as a, okay, consistent. Again, by using some set of premises, if you are going to derive to false, so then it is going to be called as a inconsistent. And Coming to this contradiction, which we know already, okay, by using some set of premises, if you are going to, that is deriving it to false, okay, so then it is also known as inconsistent as well as contradiction. But here, in the contradiction means, so there will be some conclusion that we need to prove, but finally we will conclude that that will not be possible to prove by adding or by deriving into the false statement. So now let us see the small example related to this. Let us here the statements are given like this. Now these statements, first what we have to do is we need to represent by means of propositions. After that, these statements, what are the 1, 2, 3, 4 statements are there, they are represented like this. Okay, E implies S implies H, A implies negation H, E and A like this. Now this can be, what we have to do is we need to check out whether, so this is actually the conclusion and these are actually the hypothesis. Now by using these three hypotheses that we have to check whether this is possible to prove or not. Actually this is example for inconsistent, so that finally it is not possible to prove. So we'll get, see here the final result is E and A, negation of E and A. So that negation P and negation P becomes false only. False means it is contradiction, so that it is inconsistent. So like that we can prove this. So here I can use rule P, rule T as usually what we shown previously. And coming to this indirect method of proof, it is also called as a proof by introduction. So what is the basic idea behind this is, given any formula, we need to assume that, or given any hypothesis, that is H1, H2, H3, by using three hypotheses, we need to prove it as a, let us some conclusion. So in this indirect method of proof, what we'll do there is, so this conclusion, we'll assume it as a negation for this, and that will be added with your as additional premise. That means H1, H2, H3, H4 becomes your negation conclusion, negation of your conclusion. Now by using this H1, H2, H3, H4, finally we need to derive it as a false. So then I can say that whatever the initial assumption we made, that is becomes your false. Okay, so that the given conclusion is true only. So that is the process what we have to do. Again, we will follow this rule P, rule T, the formulas what we know already. And coming to this predicate logic, okay, up to now whatever we discussed, that all come under propositional logic. Now here it will come under predicate logic. So what is the difference between the two is, so in the propositional logic we have only variables like a P, Q like that. Okay, so P means I can write that John is a bachelor, Smith is a bachelor like that. Now whereas here in the predicate calculus, with the proposition there will be some variable P of X or Q of X. So like that a variable is included here, a propositional variable is included here. So let us see this example. We have John is a bachelor, Smith is a bachelor. So actually is a bachelor is a common property for both. Instead of writing the two statements, I can write with only one statement P of X. So where X can be either John for some time and X can be Smith for some time. Okay. Now if you are going to represent like that, then it come under predicate logic. And coming to this, this is a quantifiers. Normally in the predicate logic, every statement will be combined or linked with the quantifiers. Okay, we have two types of quantifiers are there, universal quantifier and existential quantifier. So whenever we need to represent the statements like for all, everything, so like that statement, if you want to combine with the predicate, then I'm going to use this universal quantifier. And coming to this existential quantifier, so if you want to represent there exist very few, at least one such kind of statement, then I'm going to use this there exist quantifier. For all means I will use the symbol like this, and there exist means I may use the symbols like this. For example, see here, all human beings are mortal. Here we have the all, so that it can be represented with the help of universal quantifier. Similarly, there exists x such that x square equal to 5. So here there exists we got there, so that I can use existential quantifier and it can be represented like this. And variables, here we told that we may use a predicate variable. So this variable of two different types, either free variable or bounded variable. So in the simple terms we can say that free variable means if it is not associated with any of the quantifier, then it is called as a free variable. Bounded variable means if it is linked or associated with any of the quantifier, then it is called as a bounded variable. Let us see this examples here. So here this is for all x, p of xy. So here x is a variable which is bounded with the universal quantifier, so that it is a bounded variable, but y is not related with any quantifier, so that it is a free variable or free occurrence. So here x, for both it is bounded variable, and here for all x, p of x, x is a bounded. Similarly, there exists y, r of xy. So y also bounded variable. Okay. So like that I can consider as an example. And here in this predicate calculus, we will use the formulas like this: rule US, rule US. So these formulas we will use to remove the quantifier from the given predicate, and rule EG, rule UG, universal generalization, existential generalization. So if you want to add a quantifier, either universal quantifier or existential quantifier, we are going to use these two rules. And these are the equivalence formulas which we can use to derive our inference theory for predicate calculus. Okay. And see the last example, the last one. Suppose we may found the problems like this. Okay. So we need to prove that there exists x m of x will logically follows from the premises for all x h of x m of x, and there exists x h of x. So this is simple as we discussed previously. Only thing is we will use rule P, rule T as usually. In addition to that, we are going to use this rule ES, rule US, rule GS. Okay. So to add the quantifier and to remove the quantifier, we are going to use this particular four rules: rule US, ES, rule EG, and UG. Okay. So this is regarding the inference theory related to the predicate calculus. Okay. So this is all overall just a basic idea regarding this particular uh, mathematical logic for first order. Okay. So in the next session we'll discuss the related to sets. Okay. And after that, in the third session, we'll discuss the previous problems from mathematical order, mathematical logic, and sets. Okay. So is there any doubts in this regarding this?